All right, now let's talk about some historical substitution ciphers. First of all, we're going to talk about monoalphabetic ciphers, and mono meaning one, and a monoalphabetic substitution cipher uses one output alphabet. There's one translation. A polyalphabetic cipher is going to use multiple alphabets. We're going to start with monoalphabetic ciphers. Okay, and the classic monoalphabetic substitution cipher is called the Caesar cipher. Caesar probably didn't invent it, but he's the one who's associated with it. And the idea here is we're going to substitute one symbol from the plain text alphabet for another symbol in the ciphertext alphabet. It's monoalphabetic because there's just one substitution alphabet used, and the classic Caesar cipher is a left shift of 3. Okay, so what that means is that A is shifted left by 3, so Z, Y, X is the shift, and B then would be Y, and C would be Z, and D would be A, and so forth, until Z is left shifted 3 to W, right? Okay, so then if I want to encode with Caesar, attack at dawn, it would be A is X, okay, X, T is Q, so TT, A is X again, CK at the end of attack, C would be Z, as you see here, and K would be H, as you see here. So that's attack, and at dawn is the rest of this. Okay, so that is the Caesar cipher. This is also the secret decoder ring cipher, right? Because we're just converting one letter into another. So let's talk about Caesar's power. Well, the key, if Caesar had a key, it's a shift value. So you could imagine saying, Caesar, we're going to shift +3 and the plain text to get the ciphertext. And if we did Caesar +5 and a plain text, we'd get a different ciphertext, right? The key is essentially the shift value. Pros of Caesar, it's super easy to perform, right? We can do this right here. The con is it's super easy to break. The entropy or the randomness of the text is never changed. A is always X, B is always Y, C is always Z, and so on, right? So if you look at this, you see a letter followed by a double letter, followed by the same first letter, followed by 2 other unique letters. So, we could say, what could we learn about the plain text here? Well, the first and fourth letters are the same. Second and third are the same. Okay, and double. And then we've got these last 2. Well, how many letters in English are doubled? How many words have a double letter in 2 and 3? And the first and the fourth letters are the same. Pretty soon we could rule this out to probably attack, or a small number of other words that fit that model. Okay, that's the structure of the text being revealed, and Caesar does not hide it. Okay, another thing is that once you solve one letter, you have one fewer letters to solve. Okay, so another way we might look at this is to say what letters are the most common here. QQ shows up, or Q shows up several times. T is a very common letter. Once we decide that these Q's are T's, then we only have to figure out the positions of 25 letters. And when we decide that X is A, 24 letters, and so on and so forth. So as we break the cipher, it gets easier and easier to break, and eventually it falls apart. I mean, some people break Caesar ciphers for fun. Okay, this used to be called the jumble. All right, that's the Caesar cipher. Now there's something called this keyed Caesar, and this is a slight variation on the Caesar. So there's a key word instead of a shift value, and that keyword is going to modify the substitution alphabet. So what we do is we place the keyword first, and then we skip repeated letters. Okay, so if the key is horse, I write HORSE at the beginning of my substitution letter, or substitution alphabet, and then I do the rest of the letters. A, B, C, D, skip E because we've already used it. F, G, skip H because we've already used it. I, J, K, L, M, N, skip O because we've already used it. P, Q, R, S we used, and then the rest of the alphabet. So now if I wanted to write, let's say, attack, okay, A is H, T is T, A is H again, C is R, and K is G. Okay? Still a monoalphabetic cipher, because there's just one output alphabet. Still poor diffusion, right? Because the plain text structure is reflected right here, right? These letters are the same, these letters are the same, and so on. The other problem with the keyed Caesar is that portions of the cipher alphabet will almost certainly overlap the original. So because of how keyed Caesar works, we set up horse, and this permutes this part of the alphabet and this part of the alphabet. But once we hit the last letter alphabetically, the position of S here, because S is the latest letter in the alphabet in the key, the remaining letters of the alphabet actually aren't substituted at all, right? So there's a failure of substitution there. So arguably, in some sense, it's worse. Okay, you say, why don't we just permute the alphabet completely? So we're just going to randomize the output alphabet fully. Okay, so here I've come up with a random permutation of the alphabet. There's no structure or order. Okay, well the con here, of course, is that I need to share that output alphabet with the receiver somehow. I can't just share a number. I actually have to give them that order of 26 letters. Okay, and it's also really only marginally harder to crack than keyed Caesar or regular Caesar. For a number of reasons. The first reason is we still have very poor diffusion. Okay, so if I write attack, I'm going to get X, TT is going to be MM, A is X again, C is C, it just so happened that, and K is O. Okay, so once again we have the same structure of the first two, these two are the same, and then these letters are unique. Okay, and so we're not hiding the structure at all. And the other thing is, once again, once I figure out one letter, I have fewer letters to figure out. Okay, so for example, if I said eat at Joe's, okay, and I'm going to incorporate this, or encrypt this, P, X, M, XM, Joe's would be Q, V, P, F. Okay, eat at Joe's is Q, V, P, F. So I see a bunch of repeated letters here, right? So if I assume that this language is English, I'm going to think, well, P, X, and M are going to be very common English letters. Okay? Common English. Right? Well, what are those common English letters? Okay, we're going to think about it. Well, what the most common English letter is E. Okay? So if I figure P is E, and I try that out, then I'm going to say, well, what are the other most common letters? Well, T and A are also super common. And so if I figure E, T, and A are P, X, and M, pretty soon I'm going to have figured out eat at works, right? And then I'll know what this is E. And so now I've already worked out 3 of the most common letters. I'll have solved E, A, and T. And then the rest of the letters just keep falling together, right? So even though there isn't a single shift value that I'm trying to figure out, it still has this characteristic that as I figure out one substitution, the whole thing kind of falls apart. Okay? That's a problem with a monoalphabetic cipher. This brings us to the magic words Eteoen Sherdlu. Okay? So in the old days of newspapers, when we used to print using a printing press, right, and we would put letters together, you might have wondered, well, how did newspapers get all of those little metal letters into the right place at the right time? Well, they used this gigantic machine called a linotype, and in the linotype there's this magazine, and the magazine is full of little metal letters. Okay, and a user would type on a keyboard, and as they typed, the metal letter in question would slide down and would go into the correct position. So the user would type, but instead of typing onto paper or something, they would, as they typed, the letters would slide down and fall into the slot. Okay, so I type a P and a little backwards P because I'm going to print it, right? So I need the reverse is going to slide down and ka-chunk into the spot. And then I type E, and then now an E comes down, ka-chunk, and I type a T, and a T comes down, ka-chunk, and an E, same thing, right? Ka-chunk, I can't write backwards very well, and an R, ka-chunk. And so then now, if we bind these together, and we ink them, and we print them, I'm going to get P-E-T-E-R. Okay, so that's a linotype. Now, on the keyboard for the linotype, the first two rows, okay, it would be like here and here, I believe, were E-T-A-O-I-N-S-H-R-D-L-U. And you might wonder why. Well, that's because this is generally the order of letters in English. So E-T-A-O-I-N-S-H-R-D-L-U, in that order. Okay? And so they organized it this way so that it would be faster for the writers. But what that means is when you're trying to break a cipher that you know is in English, you're going to assume for a monoalphabetic cipher that the most frequent letter is an E. Okay? And then you're going to assume the next most frequent letter is a T, and then an A, and so on. And is that always true? No. But if it's not, if E is not the most frequent letter, then probably T is the most frequent letter. And if T is not, then probably A, and so on and so forth, right? And so knowing this order of letters, the magic words, eteo and shurdlu, allows you to get a start on cracking messages, at least messages that are in English. Okay? Yeah. This brings us to polyalphabetic ciphers. Okay? So monoalphabetic ciphers, all the things that we talked about so far, have one output alphabet. But a polyalphabetic cipher has, as you might expect, multiple output alphabets. And so what that means is one symbol in the plain text can map to many other symbols in the output plain text. Usually, for a good algorithm, one symbol could map to any of the other symbols depending on the state of the algorithm. Okay? And the alphabets are going to change depending on the encryption, decryption state, and so on. In a real algorithm, that's how substitution works, is polyalphabetically. The easiest way to describe a simple fixed polyalphabetic cipher is to demonstrate the Vigenère cipher. Okay? And the Vigenère cipher chooses the output alphabet based on the key that is chosen. Okay, so I'm gonna zoom out a little bit so that we can see all of this. So a tabula recta just means a square table. So suppose our message is toast and jam, and our key is crab. Okay, the letters in the key then become shift values. So C is a shift of 2, R is a shift of 17, A is a shift of 0, and B is a shift of 1. Okay, and using the table, we can do the encryption. So T plus C, a shift of 2, is going to become V, T-U-V, right? O plus a shift of 17 is going to become F, okay, because of modular arithmetic, right? We're going to, if you add 17 to O, you're going to wrap around the end of the alphabet and go back to the beginning. So that's modular arithmetic, right? A plus A, and A is a shift of 0, is going to still be A. And so it doesn't actually change A there. And now you can say, oh, well, A's are always just going to be A's. Well, no, because later, see, we have C-R-A-B, and now we're going to restart our key. C-R-A-B, 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 C-R-A-B. We would go as long as we needed to. So this A is added to A to get A, but this A has R added to it to get R. This A has R to get R. Again, this A has B to get B, and so on, right? So each letter doesn't always have the same output letter, okay? And so the shift values repeat for each input letter. We're going to repeat the key over and over. And using the tabula recta, we can encrypt and decrypt. So T plus C, so if I start at T and I add C, I'm going to get V. Okay, and if I start at O and I add R, I'm going to get the intersection of O and R, which is F. Okay, and so I can reverse that process to decrypt the message. All right, so what do we see? Well, sometimes the same letter is encrypted differently. Okay, like G, eggs, here we have B, C, and so we get HI, so different letters. Sometimes it just turns out that the same letter is encrypted the same way. Okay, but again, you would expect that to happen with some randomness, right? If we were doing this randomly, sometimes a bit is changed, sometimes a bit is not changed. In this case, these two A's both end up as R's, but maybe that's okay. All right. Now, let's see if we talk about weaknesses. Would a longer key be better? Why or why not? Well, a longer key would be better, okay, because the longer the key, the less frequently we're going to have repetitions, okay? So I'm going to type this out here, okay? Longer key, less frequent repetition of substitution, okay? Now, what else do we see about this? Is there anything weird about A in the input or in the key? Yes, there is, okay? Here's the problem with A. A has a shift of 0, okay? So if A is in the plain text, then the key is revealed, okay? And if A is in the key, then the plain text is revealed, okay? Does that make sense? So when we see an A in the plain text here, what happens is the A in the key is revealed, okay? If there's an A in the key, then what happens is the N in the plain text is revealed, okay? So this is exactly what Shannon was talking about with no bad keys or plain texts, okay? Because what if I had the key, you know, what if I had the message, you know, super secret codes, okay, and my key was okay, what am I going to get out? I'm going to get out super secret codes, right? So that doesn't help. Or what if my message was okay, and the key was super secret key? Well, what we're going to get out is super secret key. Okay, so Vigenère has this horrible characteristic that this will leak out. It also has this characteristic that the shorter and worse the key, the easier it is to crack. Of course, you know, here I'm using a key that's one English word. Okay, how hard would it be to try all the English words? Not that hard, right? It's not really a random key. Okay? What happens if we reuse keys over time? Well, if we reuse keys over time, then we're going to see more and more of these letters leaking out from A's and B's and things like that. And so if we reuse the keys over time, eventually someone will be able to analyze the messages and find patterns. Okay? Many polyalphabetic ciphers exist in the modern world. The German Enigma in World War II was polyalphabetic. Modern ciphers such as AES are polyalphabetic ciphers. They do not use a fixed table like the Vigenère cipher. But Vigenère is nice because it's easy to demonstrate, easy to understand. All right, that's where we're going to end today, talking about substitution ciphers. So we talked about monoalphabetic, where there's one output algorithm or one output alphabet. We talked about polyalphabetic, where there's multiple output alphabets, and we talked about what we want them to do. Okay? That's where we'll stop. Thank you.